In this video, I'm going to go through a full example for using the slope-deflection equations to find the bending moment diagram of an indeterminate structure shown below. Now there are two different types of slope-deflection equations generally. You either get the sway case, where you can have translation of the joints, or you could have a non-sway case where you don't expect any translation of the joints, and the only degrees of freedom in the system are rotations. This is a case of the latter. So since the structure and the loading are symmetric for this frame here, we're going to assume that it's a non-sway case, especially because we are assuming that all of these members are inextensible. So we have no axial deformations are taken into account when we use the slope deflection method. However, if this particular structure here did have some unsymmetric loading, like for example if there was some sort of load P that had a horizontal component, then BC could shift to the right in this case, so we could have some sway, so BC could translate, and then we would have to consider this as a sway case, which is a little bit more complicated, especially since we have inclined members. But since we don't have this, then we don't have to consider that BC are going to move in the X or the Y at all. So the first step in our slope deflection analysis is to determine the equilibrium conditions that we're going to use to find our unknown rotational deformations. So our unknown rotational degrees of freedom are slope theta B and slope theta C. And since we only have 2 degrees of freedom in this problem, A and D are totally fixed, and as we said, B and C can't translate in one direction or the other, then we know that we're going to end up having to solve 2 simultaneous equations when we get to the end of our slope deflection equation. So correspondingly, we're going to have one equilibrium condition for each joint, B and C, and those equilibrium conditions are going to look like this. So we have one for each joint that we have a rotation at. So at joint B, which is right here, where we know we have some rotation B, we know that just due to general equilibrium, M, the moment in BA, and the moment in BC here have to be equal. They have to add up to 0. And the same is true at joint C. So MCB and MCD, so that's the moment at the end of C, moment at the end of BC at joint C, and moment at the end of CD at joint C, when we add those together, have to equal 0. This is just like taking moments at a cut, and we know that the moments at a cut have to be equal and opposite. So these are what we're going to solve. In order to find these individual moments, we're going to use the slope deflection equations. But first, we're going to find some of the inputs to those slope deflection equations that we're going to need later on, and it's kind of good to find these up front. So the first of those are the fixed end moments for each of the elements. And the fixed end moments are the moments that would be caused at the end of a member due to loads that are in between the two ends, as if each end was fixed. So if we look at AB, we have, if we fixed the AB at B and we fixed AB at A, we would get no moments at the fixed ends because we have no loads in between those two nodes, or between those two joints. Same with CD, but for BC, if we consider B as fixed and we consider C as fixed, and we add this distributed load in between them, we know that we're going to get a reaction moment at B and at C, and that's the reaction moment that we're finding when we're trying to find the fixed end moments. So again, for AB and BC, we have 0 fixed end moment. So all of the fixed end moments for those equal 0. So AB is the moment at end A of member AB, and BA, FEMBA, is the moment at the end of member AB at B. So the first one here is which end of the member we're talking about, is the first letter. Then for BC, which has the distributed load, we know that the fixed end moment is going to be WL squared over 12. And that we usually get from a table of fixed end moments, and that includes a bunch of fixed end beams that look like this with different loading conditions on them. Usually you find those in the back of your textbook. So if this has a load of W and a length of L, then we know that these reaction moments here at both sides are going to be WL squared over 12. and WL squared over 12 in opposite directions. So if our unit sign convention looks like this, where to the right and up and counterclockwise is positive, then the one on the left here would be considered positive because of counterclockwise, and the one on the right would be considered negative because it's clockwise. So for MBC, which is, now we're looking for BC, so starting at B is the one on the right, and we find WL squared over 12 is 30 kilonewtons per meter times L, which is 7 meters squared over 12. We get that FEM BC is equal to 122.5 kilonewton meters, and it's positive, and it's counterclockwise. Likewise, FEM CB is going to be negative 122.5 kilonewton meters, because that's clockwise, just like this one here. So the next thing that we're going to need to know for our slope deflection equations are whether there are any chord rotations. And these are usually can be caused by support settlements, for example, or another time where you have to use the chord rotations is when you have a sway case, which we don't have. So we don't have any support settlements, and we don't have sway, so we have no chord rotation. So we can say that psi, which is the chord rotation, of AB equals psi of BC equals psi of CD. So for each member, that chord rotation is 0. So now knowing these things up front, we can find our slope deflection equations. So for a general fixed condition where both ends of the member in reality are fixed and there's no pin at the end of a single member, then we use this slope deflection equation for fixed, which looks like this in the general form, where n is the near side of the member and f is the far side of the member. So this gives us the moment at one end of the member, at the near end, based on the rotation of the nodes at the near and far ends, and the chord rotation and the fixed end moment. So we know the fixed end moments, we typically know the chord rotations, and our joint rotations, theta n and theta f for the near and far side, are generally our unknowns. And we're going to solve for those using the equilibrium equations after we sub these slope deflection equations in. So we can find a slope deflection equation which gives us moment in terms of the end rotations for every single member at each end. And we might as well find them all, even though we only need 4 of them for our equilibrium equations. We might as well find them all because we're going to need them later anyways when we want to find all the moments once we already know what those chord rotations are. So let's start with MAB, which is the moment at this end of member AB. So it's at the A end of member AB. So then in this case, A is the near side and B is the far side. So if we just sub those in first, and I'll do it explicitly for the first one, we get 2 theta A plus theta B minus 3 times the chord rotation plus the fixed end moment at end A of member AB. So in this case, we know that theta A equals 0 because that's a fixed end, so that means we can't have any rotation at A. So theta A equals 0. Theta B is an unknown. The chord rotation is 0, and the fixed end moment is also 0 for this case. So then if we sub in L, we're going to get 2 EI over 8.6, which is the diagonal length of this member. So let's just put that length in here. Okay, so we're looking for the length of the member in the axis direction of the member. Okay, so that's the total length of that member is 8.6. And then we're going to end up with theta B as being the only thing that's left here. So then we can work that out. We can divide this, and I'm going to leave things in terms of EI. So we get 0.233 EI theta B. And then we can do the same thing for MBA. So theta A again is 0, the chord rotation is 0, FEM is 0. So now we get, again, MBA in terms of theta B, which is 0.465 now. Then for BC, it's a little bit more interesting because now we have a fixed end moment. So I have 2EI over 7 is the length. We're looking at BC now. So we're looking at this one with the fixed end moments at either end, which we determined here were 122.5 and negative 122.5. And so we get 2 theta B plus theta C minus 3 psi plus FEM BC. So that's FEM of member BC at end B. Okay, so this one is 0. Theta B and theta C are still unknowns. So we're going to get 0.571 theta B plus 0.286 theta C. Okay, so that's just multiplying these out. This is 4 over 7. This is 2 over 7. And then plus the FEMBC, which is positive 122.5. Now it's very important that when you're doing these problems, you make sure that you have the right positive or negative sign in front of each of these. Okay, if you have a negative chord rotation, you have to use a negative. If you have a negative FEM, it has to come in negative, because if you make one mistake anywhere along the way in your slope deflection equations, your final answer will be completely wrong. So then let's do the other end of this member. And that's going to come out to 0.286 theta B plus 0.571 theta C minus 122.5, because this is a negative fixed end moment because it was clockwise. And likewise, we can get MCD and MDC. And I just missed those EIs up here. So this is EI theta B, EI theta C, EI theta B, EI theta C, and these ones are EI theta C. So you can see there's kind of a symmetry here. MAB and MBA, right, are very similar to MCD and MDC, except we have theta C instead of theta B. And MBC and MCB also have this kind of symmetry here. And this comes out of it being such a symmetric problem. So now that we have all of our slope deflection equations, which give us the moment at the end of each member based on the rotations at the end of the member, now I can apply those slope deflection equations to the equilibrium equations. So you'll recall that we have equilibrium equations up here, MBA plus MBC and MCB plus MCD, both equal to 0. So if I start with the first one, I have MBA plus MBC equals 0, and I go up to my slope deflection equations, and I find this, and I plug it in. There's MBA, there's MBC. I'm just going to plug those in here. So here's MBA. These three terms together are MBC, and then I can simplify. And now I'm going to do the same thing for the second equilibrium equation, which was MCB plus MCD equals 0. So I'm going to again take those from here and plug in the results and simplify. So now I have two equations, one here, and two unknowns, theta B and theta C. Now I can solve these two simultaneously. I'll do that just by, first I'm going to rearrange this second equation in terms of theta B. And then I'm going to take that result, sub it back into 1, and then I will be able to solve for theta C. And then so I'm just going to solve for EI theta C, so I'm going to leave EI as unknown, and I get 163.4, because I can easily sub in now EI theta C into my moment deflection equations. So I sub this value back into the equation for theta B here, and I get EI theta B is equal to negative 163.6. Now, since we have a symmetric case, we would expect the rotation at C and the rotation at B to be identical, but they're not quite, just because of round off. Well, one should be positive and one should be negative. So now we have solved effectively. We know EI, right? We're just going to leave it in terms of EI. But we've solved effectively for the rotations theta B and theta C. And now we can sub those back into the moment, the slope deflection equations, to find our actual moments. So for example, if we go to MAB, way up here, MAB is equal to 0.233 EI theta B. So EI theta B is negative 163.6. So we can say MAB equals 0.233 think it was positive 0.233 EI theta B. 0.233 EI theta B is negative 163.6. So therefore MAB is equal to negative 38.1 kilonewton meters, and since it's negative, that means it goes clockwise. Then we can do the same for all of the other slope deflection equations. So this is just subbing in these values again inside the slope deflection equation. So for BC, for example, I have two terms where I need to sub in, and then I find the answers. Positive means counterclockwise, negative means clockwise. So I've indicated the direction here as well. And you can see that there again is some symmetry here, which we expect because this is a symmetrical structure. So now we basically know the whole story because we have all of the moments. So if we draw our structure again, we can draw it with the moments on. I can explode the structure into the different pieces. Now if this is AB, okay, and this is BC, and this is CD, okay, now I can actually just draw those moments on here. So at A, MAB is 38.1, which is clockwise, so that means it looks like this. 38.1, MAB is also positive 76.0, 76.0, right? This one is BC, which is positive, which means it's counterclockwise. This one was negative, which means it's clockwise. CB is negative, which is clockwise, 76.0. And we have the other two over here that look like this. Now I've left out the shears here, but let me draw in the external force. And the only external force here is the uniformly distributed load. And then I can look at finding the shear for this. So if I want to find the shear for this beam here, I'm going to find that it looks like this. And I just can use the equilibrium of BC to find these shears. Okay, this is 105, and this one also is 105 kilonewtons. Right? So if I wanted to find this one, I could take a sum of moments about B. So if this moment is involved, the shear is not involved, so that this moment is involved, this moment is involved, these two actually cancel out because one's positive and one's negative. And then all I have left is the moment caused by this uniformly distributed load, which is 30 times the length, which is 7, times the moment arm, which is 7.5. So we have an effective moment like this. And then I can find the unknown shear here, which is 105. Okay, so since the other two are easy, I'm just going to draw the shear for BC, since it's going to help when I'm drawing my moment diagram. And the shear looks like this. It goes up 105, right? Then it goes down because of the uniformly distributed load. It goes down linearly, then up 105, right? And if I take this whole distributed load, 30 times 7 is 210. And that's the total distance that this goes down. So 105, 105, and this is our shear for BC. And now using all this information, I can finally draw my moment diagram in kilonewton meters. And I'm going to draw it all on the same. Actually, if I break it up as well, then it'll look a little bit neater. Won't be so overlapped. Okay, so for these AB, right, this is pretty easy. We know 38.1, 76.0. I like to draw my moment diagrams on the compression side, so we know that the moment arrows always point to the compression side. So this is going to be 38.1, and we have a moment over here, right, that's 76.0. We know what these are because we've actually solved for these end moments directly, right? These come out of our slope deflection equations. And then there's actually no change in shear, so there's constant shear, which means that we're just going to get a linear change in the moment between A and B. Okay, if you can convince yourself of this by finding the shears at the ends of A and B, and then from those shears developing the moment diagram, but this is a pretty simple case, so I just went directly to the end. We have a similar situation over here. This is 38.1, 76.0. You see it's pointing to the compression side. This moment arrow also pointing to the compression side. Okay, and then for this system, we know what our end moments are, right? They're both 76.0 on the bottom. It's pointing to the compression side again. So this is 76.0. And then in between, we have this distribution. If I want to find the peak here, okay, I know that it's going to achieve some peak in the middle, right? Because the shear is the slope of the moment diagram. So it's going to start at a high slope, then it's going to go to a zero slope. So when it's zero shear, the slope of the moment diagram is 0, and then it's going to go back to a negative slope until we get to 76. And this total change between here and here is equal to the area of the moment diagram. So if I want to find this peak here, all I do is I find this area. So don't forget, this is, I think, 7 meters. So it's 3.5 to the half. This is 3.5, so the area of this is 105 times 3.5 divided by 2. I take that number and I add it to negative 76. So I start at negative 76, I add the area here, and I get the peak here, which is 107.8. And that's in the middle, that peak, at 3.5 meters. And then I have my entire moment diagram. And so I've successfully used the slope deflection method to solve for all of the moments in this pretty complex but symmetric indeterminate structure.